Okay, so we're going to finish by talking one last bit about matroid polytopes. And I told you that my favorite theorem about matroid polytopes was that their edges are of the form EI minus EJ. And today I want to explain to you what the big deal is about that. What is the big deal about having edges EI minus EJ? Let's go to this picture over here. So pictured in yellow is the matroid polytope of the uniform matroid of rank 2 in 3 elements. So the bases are 1, 2, 1, 3, and 2, 3. And you get something that is supposed to be an equilateral triangle. I tried to draw an equilateral, I failed, but imagine that's an equilateral triangle. Okay. So now the edges are these guys. This is E1 minus E2, this is E1 minus E3, and this is E2 minus E3. Okay. And now what I want you to picture is I want to place halfway, right in the middle of each edge, I'm going to place a mirror. So here's my mirror. And I put one exactly halfway in each edge, meaning that the image of 2, 3 under the mirror is 1, 3. The image of 1, 3 under the mirror is 2, 3. Okay? So that's what I want to do. And now imagine that these are real mirrors, and maybe there's a person here. Actually, preparing my class, I realized that it's impossible for me to draw a person. I can draw a bird. There's a bird, okay? So this bird is sitting over here, and it's looking across this mirror, right? And if it looks across this mirror, basically what it's going to see is its mirror image that's right here. That's the mirror image, okay? But the bird could also decide to look at itself on this mirror. It's a vain bird, and it really wants to check itself out. So if it looks in this mirror, then what he's going to see is his image that is down here somewhere, right? So now let's see, the eye is over here, and the beak is over here. But now, the bird could kind of look in this direction, where it could see this mirror and see this image of itself in the mirror. Or another way of saying it is, it could look at this mirror, then this mirror, and then this mirror. So there's going to be another image of the bird down here. Looks like this. Okay. And basically what we're going to do is just, so here's the real bird, but here's a virtual bird, and the virtual bird can either look in this mirror or in this mirror, and so there's another image here. So for each either real bird or virtual bird, it's just going to look at itself in the mirror in every possible way. Here I get this image. Okay. And now what's going to happen is that these are all the possible images. Now if you look at these 6 images of the bird, and you try to look at any one in the mirror and reflect it, then you're going to get one of the other ones. For example, this guy, if you reflect it, you get this one. Across this mirror, you get this one. And across this mirror, you get this one. Okay? So these are all the images. Now, I was also preparing my class yesterday, and I did this, which I had heard is true, but I had never actually seen it. And you should go home and do it, which is do this. put two mirrors at 60 degrees of each other. And you'll see that you're going to see exactly 6 images of yourself. They look exactly like this. Okay. Now what you're going to see is that because my mirror had a frame here, so I couldn't see this image. So I was standing here, and I could see these 4 images, and I knew that the real me was here, but I couldn't see this image. But if you put two mirrors at 60 degrees, then there are 6 images of yourself. Okay? Okay, so that's nice. So if you put a mirror across the middle of each edge, and you kind of look at the kaleidoscope that you get in this way, at least in this case, you get 6 images. Here you get 6 images. And what I claim is that this is not a coincidence. Actually, if you take any matroid polytope and you do this, you're going to get a finite number of images. For any matroid polytope, well, I started with an arbitrary matroid polytope, and so the claim is that this system of mirrors gives a finite number of images. Okay. Now, when you go home and you put these two mirrors at 60 degrees from each other, you should play with changing the angle in the mirror, and you'll see what happens. For example, at 60 degrees, you're going to see that there's exactly 6 images of you. At 45 degrees, you're going to see that there's actually 8 images of you. And if you vary the angle, you're going to get a different number of images of you. Okay. But I think you've seen, for example, in elevators sometimes when there's a mirror in front of you and a mirror behind you, and they're a little bit off, they're not exactly parallel, you see that there's infinitely many images of you. And you should play with this too. Put the mirrors kind of almost parallel to each other, but not quite, and you'll see that there's many, many images of you, and as you vary the angle, you're going to see a different number of images of yourself. That number might be finite or infinite. Okay? And so this is basically the topic of today, is this kind of basically, what's the story? The story is that you can look at any system of mirrors. Now, one thing I should say is that in 2 dimensions, if you have an edge, then the mirror is a line. In n dimensions, if you have an edge, then the orthogonal thing is a hyperplane. Okay? And so what we have is that each edge is going to determine a hyperplane, and so what we have is a system of hyperplanes. And now we're going to think of each hyperplane as a mirror. Okay? So we have an arrangement of hyperplanes, and consider each one as a mirror. What happens then is that you have an operation that says if you take some point and a hyperplane, then you have an operation that reflects it across the hyperplane. Okay? And we're going to look at that's exactly what we did here. So if you take each guy and you reflect it upon a hyperplane, you get a different guy. And we iterated these things. So in other words, what we're doing is considering the group that is generated by these reflections. Okay? So here's one reflection and then another reflection. So that's a group element that says this reflection times this reflection. Okay? So let rho sub h be reflection across h. And consider the group generated by these reflections. So we have an arrangement of hyperplanes A. For each one, we get a reflection. And so now we're going to just look at the group generated by these reflections. In other words, you're going to take each point in your space and just reflect it in any arbitrary order on any arbitrary set of hyperplanes. Okay? So let's do that over here in group language. So now let's consider a point, not a bird. Okay, so this is a point V. And actually, you'll see why, but I want to let V be over here. Okay? And so I have a 1, 2. Yeah. So here's a group element. Reflect across this hyperplane. Okay? So if you take V and you reflect it across here, you get the point S1, B. Okay? Here's another one. Another group element is reflection across the hyperplane S2. So if this is V, then this guy right here is S2, B. Okay? Now, what about this one? What should I call this one? So this is the result of reflecting this guy across this plane. And you give me two answers, and I like Anna's answer better. So one answer is call this S3, S1, SV if I call this S3. But actually, the point is that I don't need S3 because this guy is the image of S2V across this hyperplane. Yeah? And so if I take this guy and I reflect it across using S1, I get S1, S2, V. And in the same way, if I take this guy and I reflect it over here, then instead of thinking that I'm reflecting across this hyperplane, I can imagine looking at this image and reflecting it across S2. So I get S2, S1, V. And then the last one, what should I call it? Well, I can think of this as taking this guy and reflecting it across using S1. So I can call it S1, S2, S1V. Right? But I could have also thought that I'm taking this guy and reflecting it across using S2. So I could have also called it S2, S1, S2V. Okay.
You're just using 2 because you only need 2 guys to generate this thing?
So, right. So the first thing is that I just proved an identity. I just proved that S1, S2, S1 is equal to S2, S1, S2. Okay? And I also proved that, I could have called this S3, but the reason I didn't label it as S3 is that I don't need to, right? What is S3? Reflecting across this hyperplane is taking V and sending it to this guy. So I can write S3 as S1, S2, S1, or as S2, S1, S2. Okay. And so the group that I get is given by generators S1 and S2, and what relations do I have in this group? Well, one thing is that if you reflect across S1 and back, you get the same guy. So that means that S1 squared is equal to 1, is equal to the identity. Let's just call it 1. S1 squared is the identity. For the same reason, if I reflect twice across hyperplane 2, I get 1. And the other relation that I have is that these guys are equal, okay? Which I can rewrite as saying, well, look at this. S1 is 2 cubed is what? It's S1 is 2, S1, S2, S1, S2, right? That's S1, S2 cubed. But now I can take this S2, S1, S2 and flip it over, and I get S1, S2, S1, S1, S2, S1. Okay. So first I took S1, S2, S cubed. S1, S2 cubed. So I got S1, S2, S1, S2, S1, S2. But then I said, now let me group it in this way. It's a group, so it's associative.
But you, it should be 2, 1, 2.
And so,
the last 3.
So I took S2, 1, 2, and I wrote it as S1, S2, S1. Because of this equality. Yeah? So I use that equality, and I get this. And then you see S1 squared is 1. So this is not here. And then you get S1, S2, S2, S1. But S2, S2 is 1. And so you get S1, S1, which is 1. So a shorter way of writing this is saying S1, S2 cubed is equal to 1. Okay? And if you think about it a little bit, you're going to see that these are the only relations. Okay? What group is this? You recognize it? So first of all, is it a billion or not? If it was a billion, it would commute. But S1, S2 is not the same as S2, S1. So it's not a billion, and it has 6 elements. So what's the only group on 6 elements that is not a billion? You guys remember? It's S3. And so this is a little unfortunate because people call these guys lowercase s's, and these guys uppercase s's. But that's S3, the symmetric group on 3 elements, permutation group. Okay. You'll sometimes see that people don't like calling this guy capital S and this guy lowercase s, and sometimes you'll see them write it like this, which is it's debatable whether that's better, but I'm proud that I can write that. I didn't used to be able to write that. But this is the group generated. Okay. Finite group. Okay. So now, well, maybe let's think a little bit about this. So in the more general situation where I have any matroid polytope, any edge from B1 to B2 is of the form EI minus EJ. And so I have a hyperplane, and the hyperplanes are purple, I guess. So to match my picture, let me put the hyperplane like this. So this is B1, this is B2, and this direction is EI minus EJ. Okay? So what is this hyperplane then? Well, this hyperplane, its normal vector is EI minus EJ. So its equation is xi minus xj equals something. And what's your guess? I'm sorry?
50-50 chance.
Well, I mean, the thing is that it depends where this guy is standing, right? Because he could be standing higher or lower. So actually it's not a 50-50 chance because it could be any constant. It could be xi minus xj equals anything. But notice this, that the origin is here. And the reason is that what is the distance from O to B1? This guy has coordinates 0, 0, 0, 0, 0, and this guy has coordinates 1, 1, 0, 1, 1, 0, 1, 1, 0. With how many ones? The rank. So by the Pythagorean theorem, if this guy has a bunch of zeros, and this guy has r ones, then this length is square root of r, where r is the rank. And by the same reason, this guy is also a basis of the matrix, so it also has length square root of r. And this hyperplane, the hyperplane that cuts through the middle, is the higher dimensional analog of the perpendicular bisector. It consists of the points that are equidistant from B1 and B2. The origin is one of them, so therefore the origin is on this plane, on this hyperplane. And so actually, if the origin is here, then xi minus xj has to be equal to 0. So this is really the hyperplane xi equals xj. Okay, so that's good news. Now, we know that these guys only differ in one coordinate, right? Maybe in, I mean, they can only differ in 2 coordinates that are saying swap I and j. And so it has to be that this is j and this is I, and this is j and this is I. And to go from here to here, what you're doing is just swapping the one from here to here. Okay? And so I'll leave it as an exercise to you, but it's an easy exercise to see that if you have point B, and if you reflect it, so here's the reflection. Let's call it rho ij of B. Then actually what this reflection does is exactly what happens to these guys. It just switches coordinates I and j. So if this guy is B1 dot 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 BI dot 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 VJ dot 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 BN, then when you reflect, you just get the same coordinates, except VJ and VI are swapped.
Sure, it makes sense with the xi equals xj.
Yeah, absolutely. I mean, the reason is precisely that one, that this is the hyperplane xi equals xj, and it shouldn't be immediately obvious, but if you think about it, you'll convince yourself. Right, exactly.
The things on that hyperplane will
That's a good way to see it. The points on this hyperplane, when you reflect them, they stay put. Right? And these are exactly the points that have coordinates I and j equal. So when you swap coordinates I and j, nothing happens. It's a good way to see it. But so this is a nice exercise. Rho ij, the reflection. Rho ij simply swaps coordinates I and j. Okay. So if I started with V, I ended with this guy where coordinates I and j are swapped. Okay. So what happens then? You have some point. V equals V1, V2, V3, V4. Let's say that we're in one dimension higher, but what I'm going to say here applies for any dimension. Okay? What happens when I swap, when I reflect across 2, 4? Well, I get the guy that swaps coordinates 2 and 4. Okay. Now what happens when I swap 1 and 4? Well, it swaps the first and the fourth coordinate. And the point is that no matter what hyperplane I reflect across, all I'm doing is moving coordinates around. Okay? And so if I started with some point, then the possible images are all just reorderings, permutations of these coordinates. Okay? So since rho ij swaps coordinates I and j, any group element which is a sequence of reflections It simply reorganizes the coordinates, permutes the coordinates. Okay. And so that immediately proves to me that my group is finite because the images are finite. They're just the permutations. Now, another thing we should ask ourselves is, can you hit every possible permutation? So I start with this one. Can I hit V4, V1, V2, V3? I need to get from here to here, swapping pairs. Okay. Now, so now the question is, what pairs am I allowed to swap? But do you remember the answer to that? If I mean the pairs I and j that I can swap are the edges ei minus ej that appear in the polytope. And we know what those are. For example, if the matroid is connected, we know that every ei minus ej appears. We proved that. So if M is connected, then every ei minus ej is an edge. So every transposition is available. And therefore, the group that I generate is precisely the symmetric group. Because I can get to any reordering by swapping two elements at a time. Now, if it's not connected, then what you're going to get is a product of symmetric groups.
So you just get the direct.
Right. So, I mean, if the matroid is not connected, then it is a direct sum. Each direct summand gives you a symmetric group, and the group of reflections here is just a product of the symmetric groups. It's finite. Okay. So what we just proved, theorem in almost. It's almost true. Theorem, the reflection group generated by the hyperplanes perpendicular to the edges of P sub m for m connected is the symmetric group on the gram set. That's really nice. That's really nice, and it's nice in one way, which is that kind of on its own, it's a nice statement. And for example, people make money by making kaleidoscopes using this idea. Okay. So let me show you an example. What happens if instead of this picture in the plane, you make the same picture but in 3 dimensions? So I started with a triangle. Now let me start with a tetrahedron. We'll see if I actually manage to draw this. It's going to be hard. Here's a tetrahedron. Okay. Now, so what are the planes here? Well, there are all the planes that cut an edge in half. This is a regular tetrahedron, so the planes that cut an edge in half exactly go through the other 2 vertices. For example, the plane that cuts this guy in half goes through the midpoint of this guy and these 2 vertices. In particular, it goes through the center of the tetrahedron. Okay? So let me say that this is the center of the tetrahedron. Okay? And so let me now make this picture right here. What I did here is, this is an equilateral triangle, and I cut it into 6 pieces. Okay? So this is an equilateral triangle. I cut it into 6 pieces, and I'm only considering this piece. That's this piece. Okay? And let me just join that with the center. Okay? So you can imagine that basically what happens is that the origin is behind the board. And if you look at the tetrahedron from here, what you see is 6 triangles, and the origin is behind. And so basically there's 6 wedges like this coming out of there. This is one of the 6 wedges. And for each one of these triangles, I have a little wedge coming out from the center. Okay? And that's true for each face. And so what you have is this picture on each one of the 4 faces of the tetrahedron. And so what you get is 24 wedges that look like this. And each wedge is really a 3-dimensional thing, where I'm afraid I'm totally ruining the picture, but I'm going to try. So this is kind of this outside face. Yeah, that's better. And then these are the two faces, so you kind of look in here.
Wait, where's that? The outside face is cutting into the middle?
Yeah, so this edge is still in the front of everything. Yeah. And so you can buy this thing. You can buy this thing, a little shape of a little wedge of exactly this shape, in exactly those angles. What happens if you make your bird standing in that little wedge and look around? It's going to be very happy because there's all sorts of images of himself. There's going to be 24 images of himself. Just like here we had 6 because we had 6 pieces. Here you're going to see 24 images of yourself. Okay? The group that you generate is the symmetric group on 4 elements. And this group has 4 factorial equals 24 elements. So that's the number of images you're going to see of yourself. And actually, since you guys who took the polytopes course last semester, and you kept trying to want to know what a permutahedron looks like, well, if you stand in there, and if the bird stands in there and it looks around, what it's going to see is a permutahedron of birds. Yeah, that's exactly what it's going to look like. And this is
the vertex.
so its head is one of the vertices, and what you're going to see is exactly the permutahedron, where each vertex corresponds to a permutation, and at each vertex there's your face. So if you're really vain, this is perfect for you. Permutahedron of copies of you. Beautiful. But so you can imagine, this is cells, of course. People like this. People like to say they don't like mathematics, but if you show them a permutahedron with their face in there, you're going to buy it. So this is nice. This is a nice fact that you can really kind of tell anyone who doesn't know mathematics, and it's a nice thing. They'll be amused. So that's one reason why this is interesting. Now, well, the point also, of course, is that each one of these mirrors is one of the mirrors of the system. Okay? For example, well, I'll let you stare at this picture on your own, because if I point here, you're not going to see anything. But I want you to notice that every mirror, every one of these 3 mirrors that constitute this wedge, is one of the mirrors determined by the polytope. So it is a mirror perpendicular to an edge. Okay?
Can I just ask, because I think I almost can see it. Every mirror essentially runs through one edge and to the midpoint of the opposite edge.
Yeah. Yeah. I mean, if
So it runs, that's not quite true. Yeah. Yeah, okay.
now you see why I don't want to try to explain it to you guys. Okay, but so that's kind of aesthetically nice, but let me also make the point that this is actually very important, very interesting mathematically. I just erased the proposition here saying that this reflection group is the symmetric group. And for any matrix polytope, you get a reflection group which is finite. And the question we should ask ourselves is how rare is that? If you pick some hyperplanes at random, is your group going to be finite? No, certainly not. Okay. So how rare is it how rare are finite reflection groups? Well, I can assure you that if you choose at random some hyperplanes and you look at the reflections, that's not finite. Okay. Now here we saw that every matrix polytopes gives us a finite reflection group, and it gives us exactly a symmetric group. Okay. Now here I give you a description of the symmetric group that is nice. Maybe you haven't seen it before. Let me give you a description of the general symmetric group. The general symmetric group is given by reflections. It's generated by reflections S1, S2, S3, up until Sn minus 1. Okay. And the relations are Si squared is equal to 1. Then any two consecutive guys have that same relation, of course. Maybe it's not of course, but you can think about it for a little bit, and you'll see that Si and Si plus 1 cubed is equal to 1, just because it is over there. And now, if you look at S1 and S3, actually those two commute, because S1 swaps coordinates 1 and 2, and S3 swaps coordinates 3 and 4. And those two operations don't affect each other. So the only reason consecutive ones have a relation is because if you swap 3 and 4 and 4 and 5, then one messes up the other one. But if the two are far apart, they don't bother each other. And so actually, Si and Sj commute, which you can write as Si Sj squared is equal to 1 for j minus I bigger than 2. Okay? And so people like to write this group in this way, is described in this way, where whenever you have, you put a vertex per generator, vertex generator, edge for any two guys if Si, Sj to the n is equal to 1, then you put I, j, and an n here. But if n is equal to 3, you forget the n. If n is equal to 3, no, you don't bother, because normally they're all 3s. In this case, they're all 3s, right? And if n is equal to 2, you don't put the edge, actually. So I can describe this group with this graph, where a graph defines a group where the generators are the vertices, and every edge defines a relation. So maybe it's even easier if I just draw. Let me draw this. A, B, C, D, and let me put 4 here, and a 5 here. So this defines a group. Generators are A, B, C, and D, and the relations are A squared equals B squared, and so on. Those are all 1. And then for each edge, you have a relation. So for example, AC to the 4th is 1. BC to the 4th is 1. CD to the 5th is 1. If you don't see a label, you assume that's a 3. And if you don't see an edge, you assume that's a 2. BD squared is equal to 1. AD squared is equal to 1. Okay. This is called the Coxeter group associated to the graph. Graph, Coxeter group.
So this is like a generalization of the symmetric.
So this is a generalization of the symmetric group, where the symmetric group is just given by a picture of some guys in a line. Okay.
With the symmetric group, Sn minus 1 and S1 don't have a relationship.
They have the relation S1 Sn minus 1 squared is equal to 1. So the reason that I bother telling you this is because I want to show to you that finite reflection groups are incredibly rare, and they're so rare that they fit right here. I'm going to show you all of them. Here's another one. So this guy is also finite reflection group. Here's another one. Okay. So this is called AN minus 1. This is called BN, BCN. This is called DN. And these are actually the only infinite families. And the other ones are this one, this one. This is called E6. This is called E7. This is called E8. Then this is called F4. This is called H3. H4. And IN, the last infinite family. Now this should be completely wild to you because we started with this geometric question that says, if I put some hyperplanes and I reflect around and I get a finite group, how surprised should I be? The point is that you should be really, really surprised because what you have in your hands is one of a very concrete list of groups. And actually they all happen to be Coxeter groups. And for all of them you can draw a picture like this. This is not obvious at all. Okay. These are the only ones. Give me just a second. The only other ones that you can build are just products of these. Okay. So let me call them the only irreducible ones. So every finite group is either one of these or a product of some of these. Okay. So what was your question?
Shouldn't it be really, really hard to actually make that actual physical thing with the mirrors that you're talking about?
Well, for example, how many of these are three-dimensional? Well, if we kind of trust our analogy, there's only three-dimensional ones here. And the only three-dimensional ones, well, maybe I'll put them here. So the three-dimensional ones. Actually, this is a two-dimensional one, right? And it has two nodes. It has two generators. If you want three-dimensional ones, they're going to have three generators. So they should have three vertices. And so what can you have here with three vertices? A2, then you could have this one, BC3. Can you have this one? That already you cannot have because you need to split into 3 branches. You would need 4 vertices. So this doesn't exist in 3 dimensionals. These don't exist. This doesn't. This doesn't. H3 is the only one. Okay. And IN is 2-dimensional. Okay. And so, as you can imagine, let's just say 3. Sorry. This picture comes from this guy, the symmetric group. S3, A2. Sorry. No, it's 4A3. It's 4A3. This is the wedge for this guy. And now the question is, how many kaleidoscopes can you build? The answer is 3. 1, 2, 3. Period. So people make money in this way by making all 3 of them. Okay. And now, so you can kind of figure out the angles. So for this one, the angles are, these two mirrors are orthogonal to each other, pi over 2, and then pi over 3, pi over 3.
So if you have any...
This one is pi over 2, pi over 3, pi over 4. This one is pi over 2, pi over 3, pi over 5.
So if your angle's a little off, you get infinitely many?
If your angle's at a little bit off, then this is a horrible kaleidoscope, and no one's going to buy it.
Trying to arrange these mirrors like this feels like you kind of see an infinite bunch of you, and then it'll be like an instant where they'll just be...
Yeah. I mean, of course, the problem is that with real mirrors, they have, after 20 reflections, you can't see anymore.
Oh, sure.
But in theory, you have to get them exactly right. If you get them off by a milli-degree, you're off. You're not going to get it. Now, this guy comes from a simplex, from the tetrahedron, right? But now you guys know that in 3 dimensions, you have these 2 other very special polyhedra, these 4 other very special polyhedra, which are regular. And they are the cube, the octahedron, the icosahedron, and the dodecahedron. If you know a little bit about polytopes, you know that these 2 are dual to each other, and these 2 are dual to each other. And the tetrahedron is dual to itself. Well, if you want to build this guy, take a cube or an octahedron, and play this game. I mean, I'll draw it for you right now. It's not easy. It's not hard. Here's the cube. And your wedge is exactly this wedge right here. From the center of the cube to here. If you want to draw this one, it's a little bit harder. What you're going to have to do is look at an icosahedron and the reflecting hyperplanes across those. Okay? And that icosahedron is going to give you your finite reflection group. And now you should be realizing that actually this is more interesting than we thought at first, because this is very closely related to the problem of classifying regular polytopes. For example, you might know that there are these other funny polytopes which are regular and higher dimensional. The 24 cell, 120 cell, and 600 cell. And the reason these regular polytopes exist is because of these 3 weird, exceptional reflection groups. Okay. And so that brings me to definition. A Coxeter matroid polytope is a polytope whose mirrors, let's call them edge mirrors, generate a finite group. And if they generate a finite group, we know that it's going to be one of these groups over here. Okay?
Okay, so any polytope.
Is any polytope whose edge mirrors generate a finite group deserves the name Coxeter matroid polytope. We know that it's going to fall into one of these classes. Okay? If we get rid of the adjective Coxeter, what we get is the ones corresponding to this picture, to the symmetric group. But you can generalize this definition to allow any finite group. Okay?
So all matroid polytopes,
Examples, matroid polytopes.
and they all are SN or AN-1.
They all give symmetric groups, products of symmetric groups. But other examples are all the regular polytopes.
So why do we put the word matroid in the name of the thing? Why don't you just say
So-
Coxeter polytope?
So before I answer that, so the point is then that these matroid polytopes that we've been studying for the last couple of weeks probably deserve to be studied in the same way that we studied regular polytopes. Okay. And this is the wider family where they fit. And so, of course, the very natural question that we should ask ourselves is, if we just spent a semester talking about matroids, then what is this stuff? So, question. And these are the polytopes. So what are the matroids? What is a Coxeter matroid? Well, so this is the answer. Right here. So the point is that people kind of know, but this is a very new area because this definition is from the late 80s by Gelfand and Serganova. You remember Gelfand and Serganova are the ones that proved that the edges of a matroid polytope are EI minus EJ. As soon as they realized that, they thought, well, this is part of a larger story. Okay? And the answer is partially is in the book Coxeter Matroids. But this is a very recent book. It came out last year, and the point that I want to make is that actually this is a very new area where almost any question is open. I mean, they can prove some very nice theorems, but we just spent a semester talking about matroids, and most of what we said this semester is not known for Coxeter matroids, where many questions are open. So one of the groups is actually writing their project on Coxeter matroids, and so we will have a very nice readable account of Coxeter matroids